Hello friends, welcome to the 18th class of this course. In the past few classes, we solved some very interesting problems based on the variational principle and the Lagrange's equations of motion. In this class, we will try to see whether the systems with the constraints, whether those kind of systems can be treated in our Lagrangian framework, or how can we treat them in our Lagrangian framework. So let's say, assume that we have, assume we have n numbers of q's. So q's are the generalized coordinates. So we have n numbers of them. That means q, it is basically a set of q1, q2, comma dot 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 q1. And we have constraint equation. So equation of constraint, it's like f alpha equal to 0, equations like that. And assume that we have m number of such equations. So it's like f1 equal to 0, one equation, f2 equal to 0, one equation, dot dot dot, fm equals to 0. So we have m number of such equations. So in that case, all these qi's, these are not independent. So in that case, QIs are not independent. That means the virtual displacements delta QIs are also not independent. So in that case, so if you remember the delta I, or the, so where I is the action, so the variation of the action that we got, like from point 1 to point 2 dt sum over I ddt of del L del Q I dot minus del L del Qi delta Qi equals to 0. So this was the variation of the action we got, and from there we assumed that these delta Qis, these are all independent. In that case, we got our Lagrange's equation, that is, this term is 0. This term will be 0 if delta Qis are independent. So that's how we got the Lagrange's equations of motion using the variational principle. But here we cannot do that because delta Qis, these are not independent. We have m number of constants equations also. So then this is not valid anymore. This is not valid anymore. In that case, we will introduce a new method which is called method of Lagrange's undetermined multipliers. So this Lagrange's undetermined multipliers, these are denoted by lambdas. It's called this lambda alphas. So this alpha index I used because for each equation of constant, we will get one Lagrange's multiplier. So there are alpha. So this equation of constants, these have alpha index. That's why I use this alpha index in the Lagrange's undetermined multiplier. So now, if we have alpha, so if we have m number of constants, equation of constants, in that case, the modified action will be the modified action will be I equals to 1.1 to L plus sum over alpha equal to 1 to m lambda alpha f alpha dt. This is our modified action. So in that case, the variation of QIs give delta I equals to from integration from point 1 to point 2 dt sum over I equals to 1 to n, because we have n number of QIs, ddt of del L del QI dot minus del L del QI plus sum over alpha equal to 1 to m lambda alpha del f alpha del eta times delta QI equals to 0. This will be the variation of the action if we introduce variation in QI. So this lambda, this Lagrange's undetermined multipliers, these are also for each constant equation, we can independently introduce this lambda alphas. So lambda alphas, those are independent of each other. Like lambda 1, lambda 2, lambda 3, those are independent of each other. So then variations of lambda alpha, if we introduce the variation of lambda alpha in this action integral, in that case, we will get these constant equations. Okay. And if we introduce the variation of QIs, the coordinates, then we will get this kind of equation. But this delta QI, the variation of QI, these are not all independent anymore. Okay. So we have n number of delta QIs and n minus m number of delta QIs we can choose to be independent. Not all of them, because we have m number of constants. And we have m number of independent lambda alphas, right? Now let's call it equation 1. Let's call it equation 1. So as lambda alphas are independent and we have m number of them, m number of lambda alphas. So for each lambda alpha, we can vary this lambda alpha as we want, and we can make this term expression 0. So in that case, for as we can choose lambda alphas independently, m number of lambda alphas independently. So this is a very important property we are going to use. Like as the lambda alphas are independent, we can choose our lambda alphas such that we can choose our lambda alphas such that m, so such that we can get m number of equations like this ddt of del L del Qi dot minus del L del Qi plus sum over lambda alpha del F alpha del Qi equals to 0, or sum over alpha equal to 1 to m. So we can have m number of such equations due to the independent lambda alphas, because we can choose these lambda alphas freely and we have m number of them. So we can make this expression 0. We can make this, so we can have this kind of expressions, m number of this kind of expressions, or we can make its value 0 by choosing our lambda alphas. So m numbers, and the rest n minus m numbers, these will be 0 because this n minus m number of delta Qi's, those are independent. So because of that, the rest of the equations, like the n minus m number of equations, those will be 0. And because we have n minus m number of independent delta Q's, then we can get n minus m number of equations such that ddt of del L del Qi dot minus del L del Qi plus sum over alpha equal to 1 to m lambda alpha del F alpha del Qi equals to 0. So we will have n minus m numbers of such equations. So basically we are getting this kind of equations, n numbers of this kind of equations, right? So m numbers of them will be because of this independent lambda alphas, and n minus m numbers of them will be because of this independent delta QIs. So in that case, again we are getting, so again we are getting n number of equations like ddt of del L del Qi dot minus del L del Qi plus alpha equal to 1 to m lambda alpha del Qi equals to 0. So remember the difference. Previously, when we didn't have the constants, in that case, we directly used the independent. So the independent, because of the delta Qi's are independent in that case, we directly made this term 0. But here we cannot do that. That's why we used m number of independent lambda alphas to make m number of such equations, and the rest of the n minus m number of equations that are taken care of by this n minus m number of independent Qis. So so these are n number of such equations, and these are the modified Lagrange's equations for systems with constants. It's a very important equations, and there are a lot of different kind of applications of this. Now, let's look at this equation a little carefully. So we got ddt of del L del Qi dot minus del L del Qi plus lambda, sum over lambda alpha del F alpha del Qi. Sum is from lambda alpha equal to 1 to n equals to 0. Or we can make it like equals to minus of it. And we can term this term, so we can call this whole term like Q, K, Q, C, K. This QCK, this term, it is basically the magnitude of forces needed to produce individual constraints. So these are this del lambda alpha times del F alpha del Qi. These are basically the constraint forces due to constraints. Because here this is the generalized force. So it is a generalized force due to the constraints. Okay. It's not QK, it is QI. So in this way, if we can find this value of QI, so we can calculate the force of constraint. But we can only go up to the magnitude. We cannot deduce the direction from this equation. So to know the direction, we need to know the physics of the problem. So remember the direction of the forces of constraint is not cannot be can't be predicted from this equation. For that, we need to understand the physics of the problem. So this is how we can treat the systems with constraints in the framework of our Lagrangian. And we can also get the forces due to the constraints. Now let's do a very simple example to understand that. Example 1. The problem statement is consider a smooth solid sphere, solid hemisphere of radius A placed with its flat side down and fashioned to the earth or fixed to the earth. Now place a small mass m at the top of the hemisphere with an initial displacement, so with an initial infinitesimal displacement. Of center, so that the mass slides down without friction. So the hemispherical surface is frictionless. So the problem looks like this. If you can draw it, solution. So if you can draw it, let's say is the hemispherical the solid hemisphere. So, and these are the axes. Z axis, X axis, Y axis. Or let's say this is this is our X axis. So now here initially we had the object of mass m. So this hemisphere, it is fixed on the ground. It is not moving, it cannot move. And so here we have this object, small object of mass m. So now initially, before we give any displacement, it's a kind of three-dimensional problem because it can go anywhere. Like it can come in this direction, it can come in this direction, it can come in this direction. So this small particle, it can slide any direction it wants. But the moment you give initial infinitesimal displacement at some direction, then we can treat the problem as a 2D in a 2D plane, because let's say you give an initial displacement along this x direction, along this direction, a very small infinitesimal displacement. In that case, the ball, the small particle, it will fall only on this direction. There will be no motion along this side or along that side. There will be no motion. It will only fall along this direction. So the entire motion will be in the xz plane. So we don't need to consider the whole three axes, the whole 3D Cartesian plane to analyze this problem. So let's assume that the initial displacement let's assume the initial infinitesimal displacement is along x-axis. So if it's not the x-axis, not along the x-axis, let's say if it's along some other direction, in that case we can choose our axis accordingly because we have that freedom, right? So let's assume that the initial displacement is along the x-axis. In that case, we can treat the entire motion of the particle in 2D xz plane. So in that case, our problem becomes two-dimensional. We can consider two axes, x and z. So this is our hemisphere. It should be symmetric, and let's say it is our particle of mass m, and it is given a small displacement along this axis. So after that, it starts falling, and after some time, it is at this point. Particle is at this point. So the angle made by this particle with the vertical axis is theta, and its direction from this point, from this middle point origin O, is given by r. So in that case, the equation of constant, will be r equal to a. So it is moving on the surface of the hemisphere. In that case, F corresponds to r minus a equals to 0. So this is our equation of constant. Now we need to find out the Lagrangian. So in that case, we need to find out the kinetic energy. The kinetic energy T will be half m x dot square plus y dot square. Here x is the projection of this r, this position vector of the particle, which is r, along the x-axis. So which will be r sine theta, right? Because this angle is theta and this angle will also be theta. In that case, this projection will be r sine theta, and the y component will be r cos theta. So in that case, x dot will be r dot sine theta plus r theta dot cos theta, and y dot will be r dot cos theta minus r theta dot sine theta. So in that case, the kinetic energy will be T equals to half m r dot sine theta plus r theta dot cos theta square plus r dot cos theta minus r theta dot sine theta square. It implies the kinetic energy is half m. So from this r dot sine theta, we are making it a square. So then we will get r dot square sine square theta. Here we will get r dot square cos square theta. And we know that sine square theta plus cos square theta is equal to 1. So in that case, we will get r dot square plus squaring this term will be r dot square theta dot r square theta dot square cos square theta. Squaring this term will be r square theta dot square sine square theta. And if we add them, we will get r square theta dot square. And the another term will be from this square, we will get 2r dot r theta dot sine theta cos theta with a plus sign. And from this square, we will get 2r dot r theta dot cos theta sine theta with a minus sign. So those two terms will cancel each other. So this will be the expression of kinetic energy. And the potential energy, which will be mgz, right? Uh, okay, it is not y, it's z. We eliminated that y-axis. We are in a 2D plane. We are in the xz plane. So mgz, z is the height from the x-axis, and z is r cos theta. So the potential energy will be mg r cos theta. Then the Lagrangian will be T minus V equals to half m r dot square plus half m r square theta dot square minus mgr cos theta. This is our Lagrangian. So let's call this constant equation as equation 1. Okay, we had equation 1. Let's call it equation 2. Now the Lagrangian equation motion, there are two coordinates, two variables here, r and theta. So in that case, we will have two Lagrange's equation of motion. So the first one will be ddt of del L del r dot minus del L del r equals to lambda del f del r, right? So this is the Lagrange's equation of motion if we have the constant equation. If so, we have the constant equation, and lambda is called the Lagrange's undetermined multiplier. So this lambdas are called the Lagrange's undetermined multipliers. For each constant equation, we will get one lambda. And here you can say, okay, there is a minus sign here, but we can take this minus sign with lambda. We can redefine lambda like minus lambda. So lambda will take care of that. Anyway, so we already talked that we are not getting the direction of the force of constant from this qi, from this lambda alpha del f alpha del qi. We will only get the magnitude. So we can write a minus sign here, or we can omit that. That's our choice. But if we are following one convention, we should follow it accordingly. Then if we take the derivative with respect to r dot, there is only r dot dependence here. So, and there is derivative with respect to time. So we will get m r double dot minus this del L del r. Del L del r would be minus m r theta dot square plus mg cos theta equals to, now del f del r. Let's look at f equation 2. This del f del r is 1. So we will get equals to lambda, because del f del r equals to 1. Now it implies 0 equals to 0 minus a theta dot square plus mg cos theta equals to lambda. because so it's using equation 2. So we had r equals to a, right? So r is constant. That's the constant equation we are using here. So then r double dot will be 0, r equals to a, and we got this equation. So in that case, lambda will be mg cos theta minus ma theta dot square. So remember, we will only use this constant equation after getting this Lagrange's equation of motion. We cannot use it before that because we already considered that these we will get this n number of such equations, and these are not all independent because there are these constant equations. So our equation of motion will be n number of such equations along with the constant equations. That's why we first calculated this Lagrange's equation of motion, and then we are using the constant equation. So let's call it equation 3. Now the other equation will be ddt of del L del theta dot minus del L del theta equals to lambda del F del theta. Now we know that del F del theta equals to 0 because there is no theta dependence, no explicit theta dependence in equation 2. So in that case, we will get ddt of del L del theta dot, which will be ddt of, and del L del theta dot will be m r square theta dot. It will be m r square theta dot minus del L del theta. Del L del theta will be mgr sine theta because derivative of cos theta is minus sine theta, and there is a minus sign here already. So del L del theta will be mgr sine theta, and here is a minus sign, so it will be minus mgr sine theta equals to 0. That's because del F del theta is 0. So now if we take the derivative with respect to time in the first term, we will get m r square theta double dot plus twice m r dot theta dot minus mgr sine theta equals to 0. Now if we use the equation 2 again, the constant equation, we will get m, that is r equal to a. So we will get m a theta double dot plus 0 minus mg a sine theta equals to 0 using equation 2. So we have now m a square theta double dot minus mga sine theta equals to 0. Now let's call it equation 4. Okay, let's call it equation 4. So these are the two equations of motion we have. So let's solve it. So from equation 4, we have theta double dot equals to g by a sine theta, right? Okay, let's write it here. Theta double dot equals to g by a sine theta. Now what is theta double dot? Theta double dot means ddt of theta dot, it means d theta dt of d theta dot d theta, it equals to theta dot d theta dot d theta, because d theta dt means theta dot, right? And this is just the chain rule. Ddt of some function will be d theta dt and d of that function by d theta. It's like the d theta cancels and we are getting d theta dot dt. So that cancellation is just a way to remember. It's not exactly what is happening. So we will get dd theta of half theta dot square. It's very easy. If you take the derivative, it will be 2. So half will cancel and then we will get theta dot d theta dot d theta. So in place of theta double dot, we can write dd theta of half theta dot square equals to g by a sine theta. Now this half is independent of theta, so we can take this half in the right hand side. So we will get d theta of theta dot square equals to 2g by a sine theta, and we will get d of theta dot square equals to 2g by a sine theta d theta. Now if we do the integration and we write the limit when theta is equal to 0, that means when the particle was at the top of the hemisphere at this point, that means when theta is equal to 0, theta dot or the angular velocity of the particle, that was 0. And when, let's assume that at angle theta, its angular velocity is theta dot. These are the limits of integration. And if we do the integration, then we will get theta dot square equals to 2g by a minus cos theta, and limit is from 0 to theta, which gives 2g by a minus 2g by a cos theta. That's what we are getting. So we are getting that theta dot square equals to 2g by a minus 2g by a cos theta. Let's call it equation 4. Okay, we already had equation 4. Let's call it equation 5. Now we have the value of theta dot square. Let's put this value in equation 3. Put the value of theta dot square in equation 3. Then we will get lambda equals to mg cos theta, mg cos theta minus ma theta dot square, ma theta dot square, which will be mg cos theta minus ma theta dot square, which will be 2mg plus 2mg cos theta. Then we will have lambda equals to, if we take mg common, so we will get 3 cos theta minus 2. So what is lambda? This whole term, this lambda times del f del theta, this is the magnitude of force of the constant along theta, and this lambda del f del r, this is the magnitude of force of constant along the radial direction. So we already know that this del f del theta is 0. So along the theta direction, this is the theta direction. So there is no force of constant, but there is a force of constant along this radial direction, which keeps the particle on the surface, right? On the surface of the hemisphere. So that is the force of constant along this radial direction. So in that case, the force of constant that keeps the particle on the hemisphere. So the force of, let's call it this equation 6, the force of constant that keeps the magnitude of, keeps the particle on the hemisphere is F equals to, so F of constant equals to lambda del F del R, which is equal to lambda. So then let's define it by capital F, or Q constant, let's say, generalized force. So then Q constant equals to, from equation 6, we can write mg cos theta minus 2. This will be the generalized force of constant. So now from this expression of Q constant, we can easily find out when the particle will leave the hemisphere, at what angle the particle will leave the hemisphere. So if we let the particle fall, there will be some angle, but the particle will leave the hemisphere and fall freely. So in that case, the force of constant will be 0, because it is just about to leave the surface of the hemisphere. So when the particle is about to leave the surface, then Q constant will be 0. It implies mg 3 cos theta minus 2 equals to 0, which implies cos theta equal to 2 by 3. It implies theta equals to cos inverse 2 by 3. This is the angle at which the particle leaves or loses contact with the hemisphere. Okay. It's a very interesting problem we did with the Lagrange's equations of motion. We can also do it in the Newtonian mechanics. So in the next class also, we will do some more problem with this Lagrange's equation of motion and along with the constant. So that's all for today. Thank you.